Oh, it's unmuted already. We can start. Yeah, so this week we're joined by Birendra Jha. He's an associate professor in USC's chemical engineering and materials science departments and civil engineering and civil and environmental engineering departments. He received his PhD in civil environmental engineering from MIT. He's been with USC for 9 years now. His research is centered on geomechanics and multi-phase flow, and we've invited him here to talk about his work specifically on modeling underground fluid flow with deep neural networks. So, thanks for being with us.
Thank you,
yeah, anyone can interrupt with questions in the chat or in the room.
Please feel free to interrupt me with your questions anytime during the talk. It's actually better for me. Okay, so I won't go into long introductions, but just want to mention that I have a background in oil and gas, energy sector, subsurface energy sector. I work for exploration, production, and then I moved to academia. I did research on specific problems relevant to these to this industry. And then recently I have worked on other forms of energy, but still I consider myself a geoscientist. So I stay within the realm of subsurface. So geothermal, is different from oil and gas, but still we deal with rocks and fluids in the rocks. And hydrogen from the rocks is another project I'm very interested in actively working on. Yeah, for the presentation today, I'm going to focus on carbon sequestration, which I think spans a large area across energy, environment, politics, society, everything, because it touches with climate change mitigation efforts and so on. So this slide here has a video of carbon sequestration in the subsurface in layers of rocks where we have drilled wells to inject supercritical CO2 for storing over years and decades. With the color, the heat map that you see is the saturation of CO2 or supercritical CO2 that is spreading and migrating and moving in the rock. This is coming from a simulation that we conducted in our group. So the gray colors are showing rock layers, and different shadings are indicating a property called permeability of the rock, which is how easy or difficult it is for fluid to flow through the rocks. If you have looked at the rocks up close in an outcrop, when you drive by, like these areas, you will see that they are porous and they contain space for fluid to occupy the space. So that's where we want to inject and store CO2 for long-term sequestration. So next few slides, I'm going to give a broader overview because I'm imagining about your background, the background of the audience. Very different from geoscience. So I just want to come in from bird's eye view and then focus on to my problem. This schematic shows basically underground geologic systems as used for energy extraction and waste disposal, and then now carbon sequestration. I hope you can imagine you can look at the picture and imagine how it is in the subsurface. The length scales are in kilometers, tens of kilometers horizontally in the X and Y direction, for example, and in the vertical direction, about 5 to 10 kilometers depth. And you can also see offshore context with the blue water shown on the top left. Because oil and gas activity, as you might know, it is on land as well as offshore. And the rock layer geologic systems are shown with red, blue, yellow colors with grades, which is coming from simulation, underground, below the seabed or below the ground surface. And then on the ground or on the seabed or on platforms in offshore operations, you have all these pipings and rigs and other structures to inject, store, and process fluids. Yeah, so the point of this slide is that it's It's a huge industry for century plus history, legacy, a lot of research and science, and people, right? People working there. And the point of all this is to extract energy that drives our society, and then where to go from here with the climate change issues, and how we can use the same knowledge and technology to deliver on those goals, right? Natural hydrogen is another thing that has come up recently. How can we transition to cleaner fuels, not hydrocarbon based, but hydrogen, which, when you burn hydrogen, all you get is water vapor, so not a greenhouse gas, but not as potent as carbon dioxide. Water vapor is still a greenhouse gas. And then we use subsurface for groundwater resources. Drinking water comes from there, right? Disposal of industrial waste and radioactive waste. We go back to subsurface to dispose these things. Now CO2 sequestration. Okay. This one is a picture of such an outcrop that I mentioned earlier. You may have seen something similar when you drive on highways or parks, national parks. So some of the problems with the subsurface, right? It's very expensive. Capital cost is very high. You have to drill wells, which is expensive, and go from anywhere from $5 million to $100 million per well, depending on where you're drilling. And then all other processes after that: completion, logging, measuring properties of rock and fluid. So therefore, numerical modeling and simulation has played a key role, because you can't really make mistakes in the real subsurface. The costs are way too high and risks are way too high. So we have to simulate a number of scenarios, know our physics, know our outcomes, and deal with the uncertainty that subsurface presents, because really we can't see or touch the subsurface. It's like working with space. You have remote sensing, and similarly we have similar technology in the subsurface. We have to remotely sense and operate the system. The numerical modeling plays a crucial role in decision making, every aspect of the industry. That's where I work. There are many challenges in numerical modeling. I come from physics, and then being in computation. So physics itself poses lots of challenges. Physics of fluid flowing through these pore spaces is complex. You have CO2, you have brine, the salty water, and then phase change, temperature change, pressure change. Rocks can fracture. Earthquakes can happen if you raise pressure too much. All those processes have to be simulated accurately for decisions to follow. And the recent promise of AI has been very exciting, to say the least, in the subsurface community. The ideas that we are pursuing are as follows. We can use research from AI field to simulate the underlying physics faster. Faster is the key word, because the traditional methods based on finite element simulation, finite volume simulation are super slow for realistic three-dimensional subsurface systems, which, by the way, the time scale is also decades. CO2 storage, it goes on for years and years. So we have to store gigatons to prevent climate change. So given the time scale, length scale, traditional methods are super slow, and AI offers promise to do it faster. As well as when things are faster, you can do more of those things, right? So the problem of optimization requires running simulations many, many times for different scenarios, different uncertain realizations of the system. If the system is uncertain because we don't know the rock properties or the geology, well, we have to create all possible scenarios we can imagine. Then we have to simulate all of them. So if one simulation takes a week, imagine 100 simulations, how much, even with parallel computing, with traditional simulators, it's super expensive. So AI came in as a promising solution that we need to test. Of course, AI and machine learning are related, so it is good at handling big data. We have big data in the energy sector. You have monitoring and drones and temperature sensor, pressure, humidity, flow rate, all kinds of data coming every second, seismic data. So data is really big. AI has also shown promise in detecting anomalies, good and bad, for geology, geophysical data, earthquake, before the main event, You have precursory events. Can you look at that and detect an anomaly that an earthquake is about to happen? Things like that. So pattern recognition is actually, I would say, that's how deep learning started in 2010 when they had these cats and dogs problems and they were recognizing the faces of these animals. So that's pattern recognition in a sense, and we are trying to utilize the same thing for our context. And use those tools, AI tools, for real-time monitoring, decision-making, which leads to mitigating risk, scheduling maintenance, techno-economics, and allocating where to drill the next well, how many wells to drill. Okay, so now getting a little bit deeper into AI, the way I'm going to present AI in this talk is deep neural networks, right? So convolutional neural networks have been backbone of these object detection and pattern recognition models, right? They have capability to recognize a hierarchy of features in an image. So in the case of a face of a human or an animal, there are layers in the network that detect at a certain smaller length scale. Let's say at the size of eye of a face. So you have circles, right? You start with lines, then circles, then two circles, then nose and mouth. That's how the face is built. If you look at the hidden layers and look at plot the weights of those layers, you will see that happening during training. So that is great. If we have something similar in our problem, as I will show for fluid flow, we can turn to convolutional neural network. We have. And then what else has happened in last, I would say, 15 years now? Yeah, 2010 to 2025. There is a lot of advancement in open source frameworks for applying these AI models and methods without having to worry about coding every single layer and optimization, backpropagation, and so on. Now it's like we don't even have to know that stuff. It's almost there because we have it in TensorFlow or PyTorch or similar frameworks. It's like a new language is born, right, to do AI. The physics, and then there has been a parallel progress in the physics community that is trying to apply AI and do research in AI. As you will see, Fourier Neural Operator, Deep Operator Network, trying to learn the essence of equations of physics, differential equations of physics, capturing them in these layer operations of neural networks. So that has shown promise. They can handle large volumes of data because the way these computations happen, as you know, is highly parallelizable because you have matrix operations, multiplications basically, and you can spread it over all cores of the GPUs. It's highly parallel. Very big difference compared to traditional finite element, finite volume method, where the most expensive step in the simulation, the linear system solve, is not parallelizable. You have to do it in sequence. You just need huge memory and fancy stuff, but still it doesn't come close to GPU parallelization.
Could you,
Yeah.
I don't know whether you're going to cover this in like the next slide, but could you talk a little bit more about the data? I mean, you mentioned images here. So is it imaging data from sensor probes, or is it actual fluid dynamics probes where you're injecting some sort of liquid, or, can you give us a sense of the types of data that are being used in these?
Definitely, yeah, good question. So the data that I'm going to use and show for this talk is coming from physics-based simulations. So it will be fluid dynamics data. So if subsurface is like a volume of rock, at every pixel I have concentration or pressure of fluid. So it is, eventually it looks like a matrix or tensor, but these data are not really measured with sensors, but they have been generated through simulations which we trust. Simulations are expensive, which I keep saying, but we still generated the data using the simulation that we trust, so we can test the promise of AI, like can it match in terms of accuracy and forecast, can it learn the physics? And once it does, then the idea is we deploy it in the field where the data will come from real-time measurement sensors. And the sensors in the field would be like wells. These wells have been drilled. There are tools there, electrical, acoustic, radioactive, that are measuring pressure, concentration, resistivity, all kinds of physical properties with time and with space. So you take that data and do inference using your AI model, which have been trained previously.
So your tensor has, the sort of three-dimensional volume plus temporal dimension?
Correct.
Okay.
Very, very big part of our problem is that time plays a big role. And I mean, when I was trying to draw analogy between, let's say, language modeling and the physics problems in physics, time being a unidirectional in the arrow of time, very special. You have causality. Past affects future, but future doesn't affect past. So it's not that there's a difference there with the language modeling. We do have some aspects of language modeling that shows up in our spatial data, which is like in language modeling, what I see is that prediction of the next word or token depends on what has been said or written before, and up to a certain memory, right? Maybe 10 words, 100 words, depends on the model. Something similar happens here. Prediction of pressure at a point in the volume depends on its neighboring pressures. So spatial analogy is there with language model, but time is a very special thing that doesn't. And I'll show you when the AI model doesn't honor time, how it breaks in a very special way that we never saw in traditional simulations. When they break, the errors are completely different. Okay, so yeah, I have lots of detail. I'll just skip through some of them, which I think is not necessary. But this one is something I use in my class to motivate how AI research progress in the AI community, computer science, language, social sciences, and other fields, how that can translate to geophysics problems in geosciences. So left column here. Yeah. So these are like, I think, well-known problems in AI: object detection, classification, face recognition, video prediction, which has a time angle, and then corresponding mapping to problems in geophysics. So pattern classification in turbulent flow, like in ocean, like oil spill in oceans, you have to predict that is turbulent flow, or climate modeling with you're dealing with atmosphere. So there are some analogies, and that's what this paper in Nature 2019 is trying to draw, and then also highlights the challenges when you do that. So we have huge volume of data. Velocity or the speed at which data comes is also high for some of the problems, some of the domains. Variety is high. Uncertainty is high. In the geosciences, that's one of the big issues. We cannot really see and measure things to the desired precision and accuracy. We have to use remote sensing and indirect means to measure quantities, and still you are limited to wells that you drill. So you don't have information between the wells. So there is large uncertainty you have to deal with. Okay, so these are some of the architectures we have implemented, played with, and improved upon in the last few years of our research. Of course, convolutional networks. Then we combined them with time series modeling using LSTM, for example, to capture time. So convolutional layers were giving us spatial patterns, and then LSTM was giving us marching forward in time. Autoencoders has been very popular in different communities working with physics problems. And Vision transformer is something we applied recently for problems in fluid dynamics, viscous fingering problems that I have to show, operator network, and Fourier Neural Operator. FNOs, we, at least last few months, I would say we are very excited about FNO and DeepONet, because there are some things with these network architectures that by design bring in physics. So it makes it very easy to bring in characteristics of the differential equations that determine the physics. For example, the Fourier layers in this FNO architecture, they are very good at capturing patterns across a vast range of length scales. So tiny fingers at pore scale, micrometer scale, all the way to kilometer scale plumes in the subsurface. Convolutional layers, they were struggling so much, you had to throw in more layers, more filters, still not able to capture the full span of length scale. But when we switched to Fourier neural operators, it was much more accurate. It worked in spectral domain. Okay, so then I have a few slides on this carbon sequestration problem, motivation and the economics of it, just to show you why the problem is big and what looking at. So here the idea is you take CO2 from coal-fired power plant, ethanol plants, instead of releasing it to the atmosphere, you capture it and then you store it in the deep underground layers where you have two choices. You can inject it into saline aquifers, which are basically aquifers that are not used for drinking water. They are just there with brine, highly salty water. You inject it there, or you inject this CO2 into depleted oil fields. There are pros and cons for both. Saline aquifers, what is the benefit? Benefit is that you're dealing with undisturbed virgin systems, so it's easier to predict in some sense properties, changes in properties, whereas in the case of depleted oil fields, you have drilled wells and you have changed many things, so you have to start with the right initial conditions, sometimes challenging. The biggest benefit with the second option, the depleted oil field, is that you get some extra additional oil as you inject CO2 into those reservoirs, which then pays for the cost of injection. Injecting CO2 is a very expensive operation, and somebody has to pay for it, even though we all want it. And that has been a biggest roadblock in implementing it the subsurface. Over the years, there have been tax credits and carbon penalties that have come into the market, but still wasn't enough. At least when it wasn't enough, people were looking at this second option. That's why we have to consider both. This is a picture of a coal-fired power plant that is actually capturing CO2 at 1.4 million tons per year rate and injecting into the subsurface into a depleted oil reservoir for sequestration plus additional oil.
What is, I guess, maybe just two questions. One is, what is sort of the capacity of that plant? And is 1.4 million tons a year the full carbon generated, or close to the?
Not full, yeah, good question. I don't have exact numbers, but usually these are, well, yeah, typical numbers are like 60 to 70% capture efficiency, because capturing takes, of course, that is also expensive. You need filters, screens, housing, and vessels. So usually 50 to 60% high quality CO2 is what we need, because if it's impure with other gases, then transportation becomes difficult because we have to cool the CO2 to bring it to supercritical condition. That's how it's injected. Anyway, so the short answer is it's not 100%. 50 to 60 to 70% is typical. But there have been like special designs where they have tried to go to 90–95% capture. An ethanol plant will be different from a coal-fired power plant. Now the economics, yeah, I won't go into detail. I thought it will be relevant, but maybe not right now. The point is that there is cost to CO2 sequestration starting all the way from capture, which is not where I work, right? I work with the subsurface geoscience when you have started injecting CO2. Capture happens on the ground, and that's totally different domain, I would say. There are cost dollar, numbers for each of these steps: compression, transport, okay, then benefit. It's a cost benefit analysis. The benefit, well, I said tax credits have been implemented in the last few years, I think 4, 5, 6 years. I think 45Q came into IRS code. Before that, it was even more difficult to justify. And then those two options, injecting into saline aquifers versus oil reservoirs, they have different benefit numbers. So the government basically prefers that companies, industry actually inject into saline aquifers, so there is no additional oil that comes out, which then is burned to generate more CO2, right? Kind of feels like it defeats the purpose. Although it's not like that when you look at the numbers, it does help the sequestration. So therefore, government gives less credit for injecting into depleted oil reservoirs versus saline aquifers. But you get extra oil from the depleted oil reservoirs, which makes up for the lack of incentives. Anyways, economics plays a big role. Where it happens, who does it. Okay, skip that. So what are the risks that we look at from long-term CO2 injection? As I mentioned already, you're going to inject gigatons of CO2 over decades. It's going to pressurize a system. So when you pressurize the system, bad things happen sooner or later. You might start breaking things. Faults may slip, earthquakes may happen. If you don't go that far, you'll start leaking CO2 from the layer where you plan to store it. Then that leaking CO2 can go into drinking water supply or leak to the ground surface. When you're planning for risk, you have to think of all these scenarios. And some places have seen some of these risks. So modeling comes essential as a tool to predict those risks and then come up with plans to mitigate those risks. Physics-based models have been used. So we can select better, less risky sites. If there is a list of sites, where do you go first? And then use the model for that selected site to predict the storage capacity at the site and risk events. And then optimize the location, number, and operation of the wells that will inject CO2, again, to minimize risk while maximizing storage, right? It's not a trivial problem. And then challenges there are the physics itself is complex. I mean, it's still a research problem. These commercial simulators don't do a good job in capturing all these physical processes at high accuracy that we need. So there has been a big gap. And AI came in, a lot of promise to fill that gap.
Is there a particular weakness of the commercial models? Are they making one weakness? Or they're just across the board?
Yeah, I listed few processes, tried to make them easy to understand, but there is movement of fluid in the rock, that is CO2 movement. Then the rock itself deforms. When you pressurize it, it's like a sponge in some ways, and it expands because of the pressure. And then it breaks because it has flaws and fractures. And that is a different physics, different equation governing that process, right? The leakage is a different equation. So when you have the differential equations, 2, 3, 4 equations, and they are coupled, they are talking to each other, it's very hard to simulate them in high resolution using finite element or finite volume. It's a research problem. It's still unsolved. Commercial simulators exist, but they don't do a great job. Often when we compare with field data, they fall short in accuracy.
Is there actually a health risk from carbon dioxide in drinking water aquifers, or is it more just?
Good question. It's not like I would say a potent toxic poison or radioactive waste, but it is a health risk. I should say that I'm not an expert on this, but it makes water acidic. And then if it happens in the subsurface, then acidity or pH decrease can further lead to reactions and dissolution of other minerals, even like a little bit of arsenic into water. That is poison, right? So I wouldn't go, so that's not my domain, but I know it is not safe, but maybe not as bad as something else. But number one reason is when we are storing CO2, we want it to stay there, not come back to us. That's the permanence of the storage is a condition for this technology to work for climate change mitigation. Okay, the physics-based models look like this. We have a box on the top left side, which is the rock volume, few kilometers in horizontal dimensions and in the depth direction, and the layer where we will inject CO2 is shown with orange or yellow color, and it has rock sitting above it, rock below it, and then wells are hard to see, but those bluish looking pixels are where wells are going to inject CO2, and this is the uncertainty or variability in rock properties that will control CO2 movement in space. permeability, and I defined its the resistance to flow or ease of flow, and porosity is the pore space, fraction of rock that is available to fluid. So given all this and this equation, that the only reason I put these equations here is to was trying to draw the analogy with LLMs, how they have this long memory problem, and that's why before transformers, LSTM and what else was there? Yeah, they were struggling to carry that memory forward, and the transformers use attention mechanism and masking to have a longer memory. One way to say it. Something similar is required here because these differential operators like the divergence here in this equation of balance of forces, it has a long range correlation. It actually correlates over the entire domain. If you take a domain, a volume, and you apply some force, you hit it with a hammer or you apply some force, it will be felt by every pixel of that volume, and that is captured by this divergence operator operating on stress. And in the fluid mass balance equation, you have time, which I introduced, brings in a special requirement. Past, affects future, but not vice versa. Okay, so we take that physics model, we generate a lot of data by placing the wells that make sense in the real world, different locations, and it should be drilled in locations where the permeability is high. And then we simulate for pressure rise, we simulate for CO2 plume, that is saturation of CO2 in the subsurface. And then, of course, rock failure, where earthquakes might happen or CO2 can start leaking because the rock has failed. So we simulate all those things and generate data. And there is an optimization framework where we define the cost function as maximizing storage, minimizing risk. And then the goal is, after you achieve that objective, the goal is to either find the best optimal locations of the injection wells, or given locations, find the injection schedule. How would you inject in that well? It's not a constant rate injection like, okay, 1 million ton per year or per whatever, 100,000 cubic meter per day. That won't work. So when we optimize, we find that, okay, you should ramp up slowly in the injection at this well because it's sitting here. And then you can decrease it when the pressure goes high enough. Then you ramp up again and so on. Finding this injection schedule is the goal. And we have to do it with hundreds, if not thousands of simulations. And that makes it very challenging, almost impossible to do with traditional simulators. Big companies like Exxon and Shell, Chevron, they have huge clusters, and that's how they have been trying to address this. And researchers who spent their entire life learning and developing algorithms for this. So that's how they have been handling this. But yeah, with AI, there is promise that we can do things faster.
On the last screen, there was a genetic algorithm. What is that? What is the genetic algorithm used for?
Genetic algorithm. Let me see. So this is the cost function, and the optimization problem here is okay. Yeah. So there are two types of optimization methods: gradient based and non-gradient based. So if you use a Newton method, you have a optimization function. You try to find the minimum by going along the slope, right? For complex functions which have many local minima, you don't want to use Newton method or gradient based method. So genetic algorithm is one such method. Are you familiar with this?
A little.
Yeah. So it's basically you generate a population of parents, and then you have some randomness in how they interact to generate next generation of children. These are all solutions, right? In this space of solutions, trying to find the optimum without forcing yourself to travel along this decreasing the descent direction, because then you will be stuck with local minima. So genetic algorithms. Okay, so time. So finally, what we were able to do is we developed a UNet model. you haven't heard of this term UNet. It's basically convolution layers and deconvolution layers, and it looks like a U shape, the way it has been drawn in many papers and literature, and that's why it's called UNet. But yeah, at the end of the day, it's just convolution layers on the left leg of the U and deconvolution layer on the right leg, and you have this concatenation shown by thick black arrow, which is crucial. That's how it gets trained faster. Yeah, if you don't, it's like residual connection, I think, but yeah, if you don't have this concatenation of the counterpart from the convolution layer on the deconvolution layer, then the training is super slow and it just doesn't get to the desired accuracy. So UNet has been very popular in modeling this type of problems. The goal is you want to recover the pressure map, deformation map, and the CO2 plume map under a supervised training method that looks similar to your DNS or physics-based simulation data. These are the details of training. I can skip that. And this is the full workflow. Okay, that too. Yeah, so that's where I will end that chapter. So CO2 storage, there are risks. It's a long-term problem. And traditional methods are struggling. They are very expensive. So we came up with convolution layer-based architecture, a UNet model, which has good accuracy. Next one is a bit deeper into the CO2 flow, and this is related to a problem called viscous fingering, which is basically the phenomenon of a less viscous fluid shown here in the yellow color displacing a more viscous fluid shown in the black color. We are injecting from left side, producing on the right side. The video looks like it's moving, the front is moving to the left because we are, the reference frame, the observer is actually moving with the fluid. That's why it doesn't look like you are displacing from left to right. But if you travel with the fluid, yes, this is how it will look like. And you see very complex fingers developing at the interface. If you did not have viscous fingering phenomenon, if you push the black fluid with the yellow fluid, all you will see is flat vertical front that is just moving to the right and diffusing, getting wider without any fingers, no complexity there. But when you have viscosity contrast, density contrast, complex fingers appear. And it's very difficult to simulate. I mean, I simulated this, I think, maybe 10 years ago as part of my PhD, and that took us like more than a month, some basic computers. So it's just not possible to do it in real life for decision-making applications. Decision you want to make here is how fast the fingers will reach the outlet, which could be a well, because that will determine breakthrough of the injected fluid, CO2 in this case, and how much oil you will produce for the enhanced oil recovery application. So it determines everything, economics of the process, storage capacity, and so on. The details of viscous fingering, skip that. We have seen this in the lab. These are all the evidence pictures. Complexity due to rock heterogeneity. Okay, so direct numerical simulation is very expensive and challenging because the equations are, again, partial differential equations are nonlinear and coupled, which is a known difficulty in mathematical physics. Solving coupled partial differential equations which are strongly nonlinear, so they have instability. So we have to use higher order methods like sixth order accurate compact fine difference. That's how I simulated this, but it took us a long time. And still, those methods, state-of-the-art research methods, they break down as the viscosity contrast grows, shown here with the red boxes. This is from the simulation. The fingers are moving. This time I'm injecting from bottom, by the way, so it's flipped. The fingers are moving to the top boundary, but at the fingertip, you have oscillations due to discretization errors from finite difference discretization. Because the process is so nonlinear, at high viscosity contrast, that is denoted by M value. So if M is more than 50 or 60, like injecting CO2 in thick crude oil, that would be the scenario. And the simulations would break. Even the best methods would start breaking, and you'll have oscillations which will pollute the entire solution space, and they will grow in time. So you can't ignore them. What we did, we tried different AI architectures, took us a year and a half, so I'm not going to go through all the failed attempts, but finally, this is the one that seemed to work. Fourier Neural Operator in a DeepONet architecture, deep operator neural network, where you have a branch net and a trunk net, concentration field. So this is the input tensor, right? This is coming from the data generated by DNS, and it goes into a supervised training of this network in the branch net, and we have parameters of the simulation like viscosity ratio, which I mentioned, crucial governing quantity, and the timestamp goes into the trunk net. Then we have Fourier layers, then we have the U Fourier layers where we invert Fourier transform, and we give back the concentration at the next time step. Okay, the detail of the FNO layers.
Is M changing over time, or is it?
Good question. No, M is not changing over time. This is the ratio of the viscosities of the two fluids that we selected.
That's okay.
Yeah, what is changing is the concentration shown with this color scale. So less viscous fluid is yellow. So here in the bottom, wherever you see yellow, concentration is 1 when you normalize it to the max, and black is where fluid is the other viscous fluid where concentration of the yellow fluid is 0. So it's a color scale of 0 to 1. And wherever the fluids mix, you have intermediate colors, reddish, orangish, right? Yeah, so M is a parameter that doesn't change. It's like Reynolds number in turbulent flow. If you have heard of Reynolds number, it is a parameter of the flow. Okay. So we did try some of the some state-of-the-art methods which have shown great promise in other fields, object detection, non-physics problems, right? So driverless cars or surveillance or something else, vision transformers, right? So they have been very popular. We tried that. I'll show you very interesting. Skip the detail. I'll show you the errors we get with these different architectures. Here. So we have four videos coming from 4 different methods. Top left is direct numerical simulation, which you can take as ground truth. We're trying to anchor to that, match that. And the top right is our best model, Fourier Neural Operator within a DeepONet architecture. Bottom left is vision transformer, and then bottom right is something called DenseNet autoencoder with LSTM for time, right? So DenseNet autoencoder is a framework architecture, and DenseNet is an expansion of convolutional neural network with dense connections. And so it ignores the pixel resolution difference. You'll see VIT as the most without. That is simply how we were able to train the networks, so the tensor size. So ignore the pixel resolution if possible. Try to focus on the movement of the yellow fluid within the black fluid. So DNS is here. What you see is that fingers develop, grow, merge, split at the tip, but you always have this bulk yellow fluid on the left side, and then you have black fluid here, which is bypassed by the fingers, and then fingers reaching outlet. In the VIT model, we have very distinct these black fluid islands that seem to propagate backward, detach from the interface, and then travel backward, which is physically unrealistic. It's impossible, and we don't see that. But it's also a type of error that we never saw with any DNS model. When DNS models break, they just have blow up of concentration to not a number, minus infinity, plus infinity. So they will stop. But VIT, on the other hand, it has these unphysical results which are still obeying laws of physics, how these black islands move like a real fluid blob will move. So it's very interesting, how it's. So we are basically calling it like hallucination of these models when applied to problems in physics, similar to hallucination of like LLM models. And we are still researching, trying to find out where in the training or model architecture it learns to do these things.
I have a couple of questions. So one, I guess, is this process stochastic?
No, the process is not stochastic, but it's like weather modeling where it's extremely sensitive to initial conditions. So it is deterministic, but even a little bit of change or numerical errors, what is it called? Floating point errors, they can also lead to different results. But it is not probabilistic or stochastic in true sense.
Okay, so I mean, like the fingers, given that you start with like a uniform surface, seem sort of arbitrary where they develop, but so the right way you can measure the quality of this is actually the exact overlap between the images?
No. So what we do, the goal here is, of course, to try to see qualitative similarity between the AI model and the DNS, but what we actually quantitatively track are called global metrics of flow. So like how much less viscous fluid reaches the outlet, the right side. We plot the concentration versus time. It's some kind of average, right? So this one and this one, which is the degree of mixing inside the domain between the two fluids. It's like mathematically, it's the variance of concentration over the entire domain. So it's a globally average metric, and that we compare quantitatively across the models. So DNS is black line, and VIT is dash dot. Then FNO, which seems to be the best, it is following the trend governed by physics. This trend of going up in the variance and coming down with time is realistic. It must happen because we know from the physics, initially fingers are created, so variance goes up, the interface becomes really jagged and lots of fingers are splitting. But later diffusion takes over, fingers merge, coalesce, diffusion takes over, and gradients are smeared, and therefore variance is declining. This is physics, and we check that with our AI models. We find that some of the other architectures, they are struggling to meet that. Yeah, so it does show stochasticity like Navier-Stokes and turbulent flow, but purely because these equations are extremely sensitive to errors and initial conditions. Let's see. Yeah, so I think I'm near the end of my talk. One thing we found, which was a pleasant surprise, is the FNO DON models. Actually, in general, all the AI models we looked at today, they are free of these discretization errors that were bothering us with the DNS method, traditional method, because there is no discretization here, right? We are not applying finite element, finite difference. We are not approximating the spatial derivative, Laplacian operator. So there is no room for discretization error. It does have hallucination type of weird errors that we are still researching, but when you can get rid of that with this FNO architecture, for example, it looks very meaningful. And that means these architectures should be scalable to high viscosity contrast, high M value, where there is no DNS solution. It's just impossible because discretization errors take over and nothing works. All these oscillations you see, this is coming from discretization. Okay. So I'm coming to the end of my talk. We discussed two types of deep neural networks architectures for CO2 problem. One for the well optimization, where the traditional methods are just too expensive because we have to do many simulations many times to capture the uncertainty. And the second one is more fine scales, closer to physics of fluid interaction and mixing, where again the simulations DNS methods are failing, either they have oscillations or they don't work. And with different architectures, we were able to overcome the challenges. And this was recently published in one of the papers. Yeah. We're expanding this work. That's all I can say.
Thank you. Thank you. Anyone has questions online, they could put them in the chat. is there, I guess you have like, maybe my perspective, there's like two directions, like increasing the quality of the FNO DON or reducing the hallucinations of VIT? Is there like, are you pursuing like both directions?
I am interested in both directions. The second problem I'm very interested in, but I'm not working on that yet. I'm waiting for some ideas and basically also talking to my student to see how excited he is. Because that's like an open-ended problem. We don't know if we will get a paper, where, when, and how. But second one, improving a model looks more straightforward. What we are doing right now is we are, so M is one parameter. There is another parameter called flow rate, at what speed you inject the yellow fluid. That varies in the field, of course, the bigger pumps, small pumps. So we are expanding the model to capture the variability in fingers and mixing for different flow rates. And the third parameter is the heterogeneity of the rock itself. And these are very important parameters because the industry cares about them. When we present a solution to them, they always ask, will it work for rock or this site and that site? So the model I showed you, that assumes one uniform, single, simple permeability. We are expanding there. Yeah.
So you've talked mainly about these expensive simulators as training data. I guess, two questions. One is, can you, now that you have these models, run them and use the simulation as sort of a verification of the predictions? And then the second question is, is there any mechanism by which these simulators can be run in the loop of training only when necessary? So like a reinforcement learning paradigm where you could run a small kind of reward function, at different parts of the training process.
That's an excellent idea. I've been thinking about ideas like that. So yeah, so we are. So when we think of real world deployment, yeah, it becomes a challenge, as you noticed, if these models are trained with data from this step, which we don't want to do, right, expensive and whatnot. So how can we justify? So I think both ideas you suggested are very, very good. So yeah, second idea you said is like, you run the simulations as a mechanism to reward the performance of the deep learning model, right? Right. Only infrequent times, and when it deviates too much from the trajectory. What was it?
Oh, just, you generate some sort of, let's say, forecast based off of an AI model,
Okay.
And running the simulator over all parameter spaces might be expensive, but once you've sort of have reduced the search space by running the AI model, you could then try to run the simulator in a similar condition and just verify in that smaller space that has been kind of carved out by the AI model.
Okay, good. Okay, thank you.
I don't know. I didn't see any questions online.
Okay.
So I think there's nothing else we can end.
Yeah.
Thank you for speaking to us.
Thank you for inviting.
Yeah.